Let's continue with our lesson. We have lesson 2.2, simplification of radicals. For our objective today, we want to simplify radical expressions using the laws of radicals that we have already discussed. As a recall, let's write the laws here. Number 1, nth root of x raised to the n is equal to x. Number 2, nth root of x times nth root of y is actually nth root of xy. Number 3, nth root of x over nth root of y can be written as nth root of x over y. Number 4, nth root of x can be written as mth root of the nth root of x. Notice that we can read these laws from left to right or from right to left. Our problem now is, when do we know that a radical expression is in its simplest form? Number 1, a radical expression is in its simplest form if the index of the radical is greater than any exponent in the radicand. Example, this one is of index 2 and we have here 8 x cubed y squared. This is not in simple form because this exponent here is greater than 2 and this one is equal to 2. So this one is not in simple form. So we need to simplify this using any of these laws. Next, a radical is in its simplest form if the radical is free of fraction or decimal. Example, this one, 2x over 5 and let's say 0.25 are not in their simple form because of the presence of this fraction and the presence of this decimal. And the last one, a radical expression is in its simplest form if there is no radical in the denominator of a fraction. Example, 1 over square root of 2 plus the square root of x is not in simple form because of the presence of this denominator. So for today, we're going to simplify these types of radicals using these laws of radicals that we have discussed earlier. Let's have some exercises. I have here square root of 81. I can write square root of 81 as square root of 9 squared, and by law number 1, square root of 9 squared, this cancels and I get a 9. What about if we have cube root of negative 125? We can rewrite this as a perfect cube and I get here negative 5 cube. And again, law number 1, this one cancels off and we have a negative. Next, suppose we have here square root of 50. Notice that 50 is not a perfect square. Therefore, we need to split this radicand so that one of the factors will be a perfect square. And that can easily be done. I can see that 50 is 25 times 2. So, here, I can rewrite the square root of 50 as square root of 25 times square root of 2. That's from law number 2. And we know that square root of 25 can be written as square root of 5 squared times square root of 2. Again, this index here will cancel out with that and we are left with 5. But square root of 2 will be retained as square root of 2. What if we have square root of 1.21? This is not in simplified form because it contains a decimal. And we know that 1.21 is a product of 1.1 by itself. So we can write 1.21 as 1.1 squared. And again, this one cancels off and we get 1.1. Let's take a look at this. If this is 2 or even number, then this should be a divisor of the number of decimal places here, which means that this can only be considered a perfect square if the number of decimal places is even. There's no way that this is a perfect square because it has only one decimal place and this one is even index. Similarly, if we have here 0.125 and this is cube root, so there's a chance that it's a perfect cube here because the number of decimal places is divisible by the index. 3 divided by 3. Now we just have to find a decimal where if we multiply it by itself 3 times, we will get 0.125. And that happens to be a 0.5. So we can rewrite this as cube root of 0.5 raised to the cube. We can now cancel this and our answer is 0.5. For the first 5 examples, we only dealt with constants here. What if we are now going to have variables together with constants as radicals? Suppose we have here 121 x squared y to the 6 and w to the 10, for example. If we do it the long way, we can apply law number 2 to split this radical into this form, y to the 6 and there. Square root of 121 can now be written as 11 squared, and then this one here is x squared. That's same index and same exponent. And we may opt to write y to the 6 as y squared times y squared times y squared. Similarly, w to the 10 is w squared times w squared times w squared times w squared and one more w squared. And we can separate this by writing them individually as this. So we have square root of y squared times square root of y squared times square root of y squared. Similarly with this, square root of w squared times square root of w squared, etc. So from law number 1, we can now have this one cancels with this, so we can now have 11 times this one cancels with that, so that's an x. And then if you will notice, this one cancels with this, so I'll have a y. This one cancels with the index there. I have a y, another y, and I have another y. And for this one, I have the first w, second w, the third w, the fourth w, and the fifth w. Applying exponent law number 1, this is product law. I can have here 11x and then a y cube and then a w to the fifth. This is the simplified form of this expression here. Notice that we can actually avoid doing this lengthy solution here by just examining the exponent of this factor here. If it is divisible by the given index, then we write it as is. These all are divisible by the given index. So, an alternative solution there would be, I can just say square root of 121 times square root of x squared times square root of y6 times square root of w10. And law number 1 will now Allow me to have this as 11 and this one is an x. Instead of applying law number 1 3 times, I can just divide the exponent of this radicand by the index. So that will be y cubed. Similarly, this will be y to the 5th. We will arrive at the same answer. You may ask, what if one of these exponents is not divisible by the given index? We can have this illustration. Number 7, for example, I will have here cube root of 250 x to the 4th, y to the 6th, and z to the 11. This is cube root of 250 x to the 4th, y to the 6th, z to the 11. Whenever you simplify a radical expression, always take a look at the given index. So the given index is 3, which indicates that we are going to find perfect cubes among all these factors here. Let's start with 250, constant coefficient. I can split this as 2 times 125, where 125 is now a perfect cube. And for the x to the 4th, I can split it such that one of the factors is a perfect cube and the remainder is there. So 3 plus 1 will give me a 4. For y to the 6, that remains as y to the 6 because this is now a perfect cube. This exponent is divisible by 3. And z to the 11 can be split as what? Z to the 9 and z to the 2. Simplifying this, I can now have 3, 1, 2, 5 times 2, and then this is x cubed times x, y to the 6, and then z to 9 times z squared. All of these are perfect cubes. Applying law number 1, we have here cube root of 125 is a 5, cube root of x cubed is x, cube root of y to the 6 is y squared, and cube root of z to the 9 is z cubed. What are left inside our radical will be 2 here, and then the x here, and then the z squared. Do not forget to copy the index. So the simplified form now is 5xy squared z cubed, cube root of 2xz squared. You may want to check whether this one is correct. The only thing that you have to do is reverse the process, which means let 5 enter the radical and it passes through a cube checkpoint. So 5 has to cube itself. So I have to cube that, and I also have to cube the x, and I have also to cube the y. So it's y6, and I will cube this also. You have z to the 9, and this one now, they will now be inside the radical sign, times 2xz squared. If you simplify this, we will get back to the original problem. Suppose we have square root of 9 over 25. This one is in simple form, so we may rewrite it, and we get square root of 9 over square root of 25. And both of these are perfect squares, so law number 1 will give us 3 over 5. Number 9. Suppose we have 6th root of 25x to the square. One way of simplifying this is splitting this index, like we have here for law number 4. Notice that the radicand here is a perfect square. So we should split 6 so that the inner index should be as a square and the outer index should be the cube. 3 times 2 will give us 6. So we get here 25x squared. Now, we can simplify this one, and this is from law number 1, this becomes 5x, and then don't forget this, that's a cube. The last one, suppose the same thing will be there, But let's say this is 8x cubed. This example has a radicand which is a perfect cube. So we cannot split this index as 3 and 2. Instead, we split the index as square root of the cube root, so that this radicand can be simplified before it has this one here. Okay, so we get the cube root of this from law number 1, that will be 2x, but don't forget, there is still a square root to that. So this is square root. That ends the simplification of radicals. We will be able to encounter other forms, a more complicated one. For example, this one here, how do we have this? We will deal with this when we go to division of radicals. Thank you very much.